Welcome to this 7th lecture on this course on computational fluid dynamics. In the previous 3 lectures we examined how to solve linear transport equations numerically, and we used the energy transport equation to illustrate certain numerical techniques. In this lecture we're going to examine a more complex problem, the numerical solution of the nonlinear, coupled, momentum transport equations known as the Navier Stokes Equations. Numerical solutions of the Navier Stokes Equations, of course, lie at the heart of computational fluid dynamics. In this first part of Lecture 7, we're going to remind ourselves all about momentum transport. We'll start off by looking how a general statement of momentum transport can be simplified by the assumptions of incompressibility and Newtonian rheology to give us a form of the Navier Stokes equations that we should all be familiar with. We'll mention that there are 2 broad approaches to solving the Navier Stokes equations. Either solving the native velocity and pressure fields with one of a number of algorithms, or by reposing the Navier Stokes equations as the vorticity transport equation. We're not going to examine the vorticity transport approach in any detail here, but it's important to know that such an approach exists. The first step to solving the Navier Stokes equations using the pressure and velocity fields will be to rewrite them in what is known as conservation form. This makes their subsequent discretisation more straightforward, and discretisation will be the subject of the next part of this lecture. So, let's start by reminding ourselves all about momentum transport. Up until this point, we've only examined physical problems that have been linear. If you think of mass transport or thermal transport, those are linear problems. This is not the case with every system though, and it is certainly not the case when we examine momentum transport, because even in the absence of such phenomena as turbulence, momentum transport is described by a coupled nonlinear set of transport equations in plural. So let's remind ourselves of what these transport equations look like. Now on the board I've put a single equation, but the first thing to note is that this is a transport equation now involving a vector quantity. If we look on the left hand side at that total derivative, big D by big dt, it's of a vector field V, not of a scalar quantity like T, temperature, or C, concentration. And so this equation now represents not one, but as many equations as we have spatial dimensions. So my velocity vector here might be 2D, or it might be 3D. So this will represent either 2 or 3 transport equations. Now, let's look inside that total derivative. Let's expand it out, and that's the term there in the square brackets. We've got rho dv by dt plus v dot grad v. What we see here is that we've got v dot grad v, which is a convection term, which of course is a velocity times a term involving velocity. And so from a dimensional standpoint, what we have in effect is a quadratic velocity term here. That's where the nonlinearity is. Now let's just draw back from the maths a second and convince ourselves that what we're looking at is actually momentum transport, and let's also recognise what momentum comes as a form here. Is it just momentum, or is it scaled by another quantity? So, recognising that every equation has to obey dimensional homogeneity, that is to say that all the additive terms take the same dimensions, let's take the simplest term here, which I'm going to take on the left hand side, rho dv by dt, and examine what fundamental dimensions describe it. Now if we think of momentum, momentum is mass times velocity, mv, fine. If we look at rho dv dt, and acknowledging that rho is a mass density, we'll see that part of the units of density involves mass, so it's kilos per cubic metre. And so if we think about density times velocity, you've got kilos per cubic metre times my velocity metres per second. And so we've got mv, momentum, but divided by a volume. So it's volumetric momentum. Now of course there's another subtlety here, because we've got time. We've got partial dv by partial dt times rho. And so what this actually describes, strictly speaking, is the rate of change of volumetric momentum. Now this is quite important, because when we look at other terms in this equation, we have to make sure that when we substitute for them, they are dimensionally consistent. None more so than when we look on the right hand side of the equation at the force terms. The left hand side of this equation physically is the rate of change of volumetric momentum. The right hand side are forces that can give rise to that momentum change. So F bar on the right hand side there are forces that act on the bulk of a material. They're what we term body forces. These can be things like gravity, or a magnetic field, or an electrostatic field. It's matter-field interactions. But let's consider carefully the units of F bar. We've already acknowledged on the left-hand side that what we have is a rate of change of volumetric momentum. So let's remind ourselves how we relate momentum to force. We've got impulse, force times time, equals momentum, mass times velocity. So force, therefore, is going to be mass times velocity over time from a dimensional standpoint. So that's in effect momentum change, or rate of momentum change. But it's not per unit volume. And so when we write our forces here in F bar, we have to take special care that the way in which they're written includes that per unit volume term. It's a rate of change of volumetric momentum, don't forget. So F bar are in effect volumetric forces. And then we've got grad dot sigma. Now sigma here is something that I'm calling total stress. We'll have a look exactly what comprises this on the next slide. And we've got the divergence of that total stress giving us a force as well. And sigma here, therefore, are not the forces that act on the bulk of a material, but act on the surface of a material. They're surface forces. So they would be things like hydrostatic pressure, shear stress, elastic forces, and so on and so forth. So when we look at our momentum transport equation written very, very, very generally, we've got momentum change with respect to time. We've got our volumetric momentum transport within a flow. We've got then body forces posed on a volumetric basis that will give rise to that volumetric momentum change. So we've got things like field-matter interactions such as gravity or magnetic fields or electrostatic fields. And then we've got that divergence of a total stress tensor, which we'll explore more in a minute. But we said physically what this represents are forces that act on the surface of a material, such as pressure or shear stress. So the momentum transport equations are not the Navier Stokes equations. The Navier Stokes equations are a special case of the momentum transport equations, and the Navier Stokes equations that you're probably most familiar with are even more a special case because it refers to a very specific set of fluid properties. Let's remind ourselves what specific set of properties we're talking about. So let's start off with our momentum transport equation, that general statement of momentum transport that could apply to any arbitrary fluid. Now, when we think about transport equations and problems, the first thing we do is make some assumptions and simplify them. And so we're going to do the same here. And we're going to focus on the right-hand side of the transport equation. And we're going to look, first of all, at my volumetric body forces, F bar. We could describe interactions with magnetic fields, interactions with electrostatics, but we're not going to. We're going to simply describe interactions with gravity. And so F bar in this case is just equal to rho g. Now, let's look at those surface force terms, those surface forces that are all wrapped up in sigma. And so I've expanded sigma out here on the board, and it's got two contributions, as we can see. We've got pressure, and we've got terms involving velocity. Let's examine them one by one. When we think of pressure, hydrostatic pressure acts on a small volume of fluid equally in all directions, doesn't it? So it will go equally in the XX direction, the YY direction, and the ZZ direction. It's what we call an isotropic pressure, isotropic force. Now, within this equation in the square brackets, excuse me, I've multiplied pressure by this thing called I. I here is an identity tensor. And if we look at other terms within the square brackets, we'll see we've got grad V and grad V transpose, which are also tensors. Now remember, we can only add scalars to scalars, vectors to vectors, and tensors of the same rank, and to other tensors of that same rank. So, we can't add a scalar pressure to a tensor shear stress. So, pressure, of course, will act in a certain direction on a certain face, inwards, hence the minus sign, and in the principal directions, and so in the XX, YY and ZZ directions, which is why we multiply pressure by the identity tensor I. That gives us a tensorial form. If we think of the other terms in this equation, we've got mu times a shear rate. The shear rate I've written in a certain way, which I'll explain in a minute, but when we think of Newton's law of viscosity, tau equals mu du by dx. Du by dx is effectively a velocity gradient, which is my shear rate, and mu is the material property of viscosity that relates to the fluid. And so I've got that exact same statement here, just in 3 dimensions. Now, in my rheology course, I've gone into a lot more detail into why we write shear rate like this, but as a brief recap, what we have in 3D is the necessity for symmetry, which is why we can't just have grad V. We've got to have something that adds symmetry to that tensor, which is why we add grad V to its transpose. If you're unsure about this, please look at the first lecture of my rheology course for a fuller explanation. What we do have inside those square brackets, though, are 2 tensors added together. If we take a step outside those square brackets, we've got the dot product with our divergence operator, and so that will give us a vector. Grad dot tensor equals vector, if it's a second rank tensor. And if we look at all the other terms in our momentum transport equation, we'll see that they are vector too. So that's rank homogeneity. We're adding the same sort of things together. We're adding vectors to vectors, we're adding second rank tensors to second rank tensors, and we're not adding scalars to tensors to vectors. So we've simplified the momentum transport equation to say, look, we've got a Newtonian fluid. Okay, let's take one more step. The final step we take is to say, let's assume that the fluid that we're dealing with is incompressible and invoke the rule of continuity. Del dot V equals 0 is the mathematical statement of continuity, or volume conservation. And when you apply that rule, del dot V equals 0, to how we expand out del dot grad V plus grad V transpose, we'll find one term disappears, and we end up with mu del squared V. And so the terms in brown on that final line relate to those surface force terms that derive from my total stress tensor sigma on the top line. Rho g is my volumetric body force, and on the left hand side we have our rate of change of volumetric momentum. And so those are the Navier Stokes equations that you should all know and love. So let's examine now the properties of the incompressible Navier Stokes equations. So here on the whiteboard I've written the Navier Stokes equations, and we can have that in either 2D or 3D depending how many spatial dimensions we elect to have in our problem. And I've also written the statement of continuity down, because all of these have to be solved together. So let's have a quick look at the left hand side to start with. If we expand out our total derivative, big D by big dt, we've got that V dot grad V term, which we've said already is effectively a quadratic term in velocity. So that's where our nonlinearity lies. If we look at the transport equation more generally, we'll see there's an additional complication here. If we compare this to energy transport or mass transport, then we'll see that we've got more than one field being transported by the equation. For example, in energy transport we just had temperature as our field. We had d by dt of temperature equal to a bunch of terms that could change temperature. Here we not only have a velocity field, which is vector in nature, we also have a pressure field, and of course we know physically that there's an intimate relationship between pressure and velocity. As one changes, so will the other. We've got gravity as well, but unless we're doing something in interstellar space which is quite remarkable, then our gravity field for all engineering purposes isn't going to change. So that's not a field we're actually solving for. We know what that is. But we don't know pressure and we don't know velocity, so we have a coupling between these two fields that also has to be solved. We of course also have more than one equation that we're solving. I've written on the board 2 equations, but of course we recognise that the Navier Stokes equations, as written here, will exist in however many spatial dimensions that we've elected to have in our problem. So we've got a set of coupled, nonlinear, partial differential equations that need solving. Now, as it turns out, the nonlinearity is surprisingly easy to deal with. The thing that gives us a major headache is this pressure and velocity coupling. Now we're going to be talking about both of these aspects in a minute or two, but we're going to start off in a second by looking at how we deal with this nonlinearity, and what we're going to do is to rewrite the equations in a conservation form, which makes this nonlinearity just a little bit easier to deal with when we come to discretisation. So let's think about our problem with coupling. Now, one of the things we can do is to just ignore this coupling and try and figure out a way in which we don't have to have two fields, which is exactly what vorticity transport does. What vorticity transport does is say, look, there's a relationship between both velocity and pressure, and also a relationship between velocity and vorticity. So if we can condense everything down to one parameter, vorticity, which I've written here as psi, then all we have to do is to write a transport equation that conserves psi. And I haven't got time to go through the maths, and I don't particularly want to go through the maths as to how you get to the Navier Stokes equation to this vorticity transport approach. You substitute these two terms in and you simplify a lot. It's going to be a bit unpleasant to code, but what it does is it simplifies the problem from a physical and numerical standpoint. You're only conserving now one field. Okay, it's still a vector field, that's fine. You just calculate psi everywhere. But then once you've calculated psi everywhere, you then back calculate what pressures and velocities that corresponds to. And so we don't have this approach where we have to couple two fields together and try and figure out how to solve them simultaneously. Now, we're not going to talk about this approach anymore here, but suffice to say that vorticity transport formulations are very efficient when it comes to solving rotational flow problems. So let's think how we deal with the Navier Stokes equations when they're written with our native variables of pressure and velocity. Now, if you're using the finite difference method, as we're doing here for illustration purposes, or if you're using the finite volume method, as both ANSYS and OpenFOAM do to solve complex engineering problems, it's very convenient to rewrite certain terms of the Navier Stokes equations in a slightly different way. And that slightly different way is something that I'm going to call conservation form. Now, this conservation form only affects how the convective terms on the left-hand side of the Navier Stokes equations are written. So let's examine that now. So here is the left-hand side of the Navier Stokes equations, rho big D by big dt of my velocity field v, which is a vector field. Expanded out, we've got rho square brackets, partial d by partial dt of my velocity vector, plus v dot grad v. And it's that v dot grad v term where our nonlinearity lies. It's quadratic with respect to velocity. And of course, it's also the convection term. So that's the term that we're going to be looking at in terms of rewriting. Now, before we rewrite it, let's just remind you of the chain rule. Look, I know you all know the chain rule, but let's look at the chain rule when we're dealing with vectors and tensors. Now, I've written here on the whiteboard a statement of the chain rule. Now, let's ignore the gradient operators and let's say what I've actually written is d by dx of ab. Well, we know that's b dA by dx plus a dB by dx. Okay, simple statement of the chain rule. Now, the gradient operator, of course, is just d by dx, but it also contains d by dy and d by dz in Cartesian coordinates as well. And so what we have to be careful with here now is the fact that we need to obey rank homogeneity. As we said a few slides ago, you can't add scalars to vectors to tensors. You can only add scalars together, vectors together, and tensors of the same rank together. A and B in this case now are vectors. And so AB, not A dot B, AB are two vectors multiplying together to make a tensor. So if we're going to take the dot product of a tensor, we end up with a vector. So del dot AB gives us a vector. Okay, let's just remember that. So applying the chain rule here, imagine that my gradient operator is just d by dx. We're going to have b grad A plus a grad B. And there on the right hand side we indeed have terms that look a little bit like b grad A plus a grad B. Now, remember rank homogeneity. We need to make sure that every term added together here is actually vectorial in nature. Grad dot AB gives us a vector. AB, when multiplied together, gives us a second rank tensor. grad in this case is a vector, d by dx, d by dy, d by dz. So vector dot tensor equals vector. So we need to put dots in the right place on the right hand side to make sure that we do end up with vectors. And so let's look at our b grad a term. Well, if we have a dot product between grad and a, that gives us a scalar. Two vectors dot product together gives us a scalar. And a scalar multiplied by a vector gives us a vector. So that's why the first term on the right hand side is grad dot a, all multiplied by b. Let's look at the second term, a grad b. Well, grad b, that gives us a tensor, doesn't it? Because grad is a vector and b is a vector. So we need vector dot tensor to give us vector again. And by tensor I mean second rank tensor. So a dot grad b will give us vector. And so we've applied the chain rule here, but also we've applied the rule of rank homogeneity. So del dot ab is del dot a times b plus a dot grad b. Okay, so it's simply the chain rule with the added complication of the fact that we've got things that aren't scalar. So if you can accept that statement of the chain rule, let's just rearrange it and let's pose it in terms of a dot grad b, and we'll see that's equal to grad dot ab minus grad dot a times b. Let's compare those terms in the purple box to what we have in the expanded part of that total derivative, particularly the convective term, v dot grad v. And so if we look at v dot grad v, that's written in the same form as we've actually just rewritten that chain rule equation. So that's all rather handy. So in this case, a is a velocity vector and b is the same velocity vector. So let's turn our attention to the right hand side of that equation, because the second term on the right hand side therefore is del dot v. Remember, for the Navier Stokes equations that we're looking at, which are for incompressible fluid flow, the statement of continuity exists, volume conservation, so del dot v equals 0. So that second term on the right hand side vanishes for the incompressible case. So we have now a relationship between v dot grad v equals grad dot vv, which is a lot easier to deal with now when it comes to discretisation, because our gradient operator comes outside the product of my terms within my vectors. Now let's put this into practice and see what it actually means for the Navier Stokes equations in 2D as we've written them. So let's say that my velocity is a vector and I'm just dealing with a 2D problem and it has components u and v. So let's see how this convective term simplifies down with this conservation form that we've just introduced. So I'm going to rewrite now in longhand what all my vectors look like. So let's deal on the right hand side with that v multiplication. I said two vectors multiplied together to make a tensor. And so on this line on the board I've got uv, which is my velocity vector, multiplied by uv, and I just multiply those vectors together and I get the tensor that I've written down, a 2 by 2 matrix. U squared, vu, uv, v squared, going from left to right and top to bottom. Okay, so the next thing we need to do is then take the dot product with our gradient. So we've got our gradient vector, d by dx and d by dy, dot producted with the second rank tensor that we've just written down, that 2 by 2 matrix, and that gives us the terms that we've got here on the right hand side of the board. And so we've got the terms in red and the terms in blue. The red is the x direction, the blue is the y direction. And note, the thing that this simplification has allowed us to do is write all our multiples of terms, our v squareds and our vus and our u squareds, inside our derivative. And if you think about what that means when we discretise, when we have our finite difference grid, we can quite easily say, well, at this node I have both u and v, I'm just going to multiply them together and then look at my nearest neighbours and take maybe a centre difference. Whereas it's a little bit harder to do that if you've got one term that might be u, another term that's dv by dx, and then taking a centre difference with that. It just complicates things. This is a far easier way of doing it. So if we look at what the total derivative actually looks like, then we can say that rho big D by big dt of v is going to be a vector, and in the x direction we've got three additive terms. We've got partial du by partial dt, partial d by dx of u squared, and partial d by dy of uv. In the y direction we've got partial dv by dt, and then partial d by dx of vu, and partial d by dy of v squared. And so these are all easily calculable terms. So, what are we actually solving when we discretise? We're solving our x-direction Navier Stokes equation, as I've written out here in 2D Cartesian coordinates. We're solving the y-direction Navier Stokes equation, which I've again written out in 2D Cartesian coordinates. And we're solving continuity, again 2D Cartesian coordinates. So these are the three equations that we have to solve when we pose our finite difference matrix, because it's going to be a 2D matrix now. Now, one of the things that we'll see is that we have to be very, very careful when we couple pressure and velocity together. We can end up with something that's mathematically correct, but actually physically meaningless. But that's the subject of the next part of this lecture. So let's recap a few key points. The Navier-Stokes and continuity equations consist at maximum of 4 coupled, nonlinear partial differential equations that involve the transport of 2 different field quantities, a vector field, velocity, and a pressure field, scalar. So this is a significantly more complex a problem than, say, solving the mass or the energy transport equation. Now, numerical solutions of the Navier Stokes equations can be computed either in terms of those native variables, pressure and velocity, or in terms of a vorticity field, where we take a combination of pressure and velocity together and repose them in another parameter, which happens to be vorticity. So if solutions to the Navier Stokes equations are computed using these native variables, these pressure and velocity fields, the first step is to rewrite the equations in conservation form, which we just have, and that allows us a great deal of ease when we come to discretisation, which is the subject of the next part of this lecture.